Okay. So I would say we can start. Hi, everybody. Today we are going to talk about Manim. That is a mathematical animation tool. It is based on Python, and it can be used for conveying complex messages that may require some complex visualization, and for which maybe a PowerPoint presentation or let's say a whiteboard and pen approach is not sufficient. So before we start, I have created a notebook that you can follow, and the link should be publicly available at the address gitlab.telecomparis.fr/ my family name, Linguaglossa, / animate with Manim. For those who are connected on Zoom, I will put it here, and then I will ask Christina to add it into the maybe the event description. Let's say that I wanted to have this presentation in a very interactive way. And in fact, here basically you will see that in the Git repository you have the Python notebook, you have a README where you can follow the installation process, which is pretty straightforward. It's an open source tool based on the work of Grant Sanderson. He was a PhD student at Stanford, and he developed this tool in Python. So I think it's nice to start with some examples, both from my library and from other people's library. So, and then we will see how these things work. So for instance, I've used it to present in a quick way what is a routing protocol. So here you can see the Aloha protocol. The Aloha protocol is a very simple protocol studied in basic networking course. You have one central station, you have n communicating stations. Communicating stations communicate wirelessly via electromagnetic waves. The messages are always acknowledged by the central station, and the missing ACK is considered a collision. And then we have a random timer if in case of a collision before sending again. And if there are multiple collisions, randomness, so typically an exponential backoff time, is used to avoid subsequent collisions. This is just an example. Another example that I've used is for showing a simple modulation. So you have a signal that typically is either an electricity, a voltage from +1 to -1, or it can be, for instance, a light pulse or something that is conveying a message. And you want to have this signal, and you modulate it with a carrier. It's typically a sine wave. It's much more complex than that. But basically, you multiply those things, and depending on the frequency of the signals, of course, you have a result signal that is carrying your original message, and depending on the frequency, you can increase or decrease the modulation parameters. So this is just a very quick introduction. We are gonna show how this works, but before, let me show something that is much more complex than what we can do today in this quick tutorial. And this is basically oops, wow, there is even the yes, there is the volume. But in this example, well, we were showing what was the it equation, by Fourier, and the visualization is super interesting because you can show not only the evolution of signals, you can show formulas, you can show how time affects the formulas. with the actual real parameters that you can modify. You can have three-dimensional graphs that convey also the time evolution of signals. And in this, what blew my mind during this presentation was that, okay, if you think about it, what is a Fourier transform? Well, a Fourier transform, if you consider a complex plane, is simply the sum of rotating vectors around the origin. So, and we can see it right here in this section, that if you consider any sine or cosine wave, any sinusoidal wave as a sum of exponential items, well, this means that if you add a time evolution of these rotating vectors, a Fourier transform can even be used to, let me show, well, to paint things in a complex plane. And well, that's actually what is happening here. And let me see if I can find this thing. Well, yes, Fourier transform is an infinite sum of of complex exponentials. So you tune the initial values, you tune all of the signs that you have done, and basically you have a Fourier transform that can be used to project into the complex plane, well, any function that you want. So your f of t can be seen as the sum of these rotating vectors, and yeah, so there is all the theory, all the explanation, and you can show that by tuning, for instance, the C of 0, that is the initial parameter, you are just offsetting by the DC value, by the constant value, and then the amount of samples that you introduce, they can affect the quality, let's say, of the reconstructed signal. And yes, so we are seeing all of those things. And so I hope that first I had your attention, and now I have your interest, because what we are going to do now is to see how these things can be made. So what we are going to do, please interrupt me if you have any question right now. I check from time to time the chat, but if you can also activate your mic and we will see what happens. Now, we will see some basics, so how Manim works, the main components that are a scene and mathematical objects, and we will show how animations are made in Manim. Then we will see how transformations can be done and how plotting can be done. And finally, we will see some advanced tools such as tracking, camera settings, and external objects. So the first thing that you will have to do is, after you install the Manim, is to import the Manim library. You can configure some media parameters like the width of the videos. You can configure the verbosity. You can also configure the quality of the animation. And in order to create an animation, well, the basic thing that you need to do is construct a scene. And how do you construct a scene? Let me add this thing. You just define a class. You have my scene, and you extend my scene from the basic class scene. Second thing that you have to do is to redefine the constructor. And to redefine the constructor, you need to pass the value self. After this is done, well, your scene is ready. So this is actually a totally valid constructors, and it's a totally valid way to create a scene. You can, for instance, do self.wait to introduce a pause in your scene. And okay, well, this is done. So after you create a class with a scene, there are two ways that you can generate the actual videos. The first way is using a Jupyter notebook. Well, if you use a Jupyter notebook, you can use the magic command Manim, passing the parameters quality with low, medium, or high values. And this is creating a 60 frame per second animation with 480p's, 720p's, or 1080p's. So let's start by low. And then you just pass the name of the scene that you want to create. Now, if I run this cell, normally what I should see is a series of actions and an empty blackboard. The empty blackboard is playing a video for just 1 second. So how does Manim work under the hood? Well, under the hood, Manim is just composing several partial animations. There are partial movies that are saved in your local file system. And basically, there is a rendering application that is under that in its underlying tools is using FFmpeg. We will see later that it is also using LaTeX to generate mathematical text. And so the rendering application is inserting by default a second of delays every time that there is animation inserted in your code. So this code is the same as having is if name equals main, then you can just have your object scene equals my scene, and then you are doing scene.render. So this is exactly the same thing. Another way, if you do not want to use the Jupyter notebook, you can still use the command line interface. So you go on your file system. Your file system is not here. Should I open another one, which is an animate with Manim? So this is my Git repository. I have introduced here a file that is scene.py. Well, this was just a simple scene. I wanted to animate the Pythagorean theorem. And well, there is a class. There is no magic command because you don't need the magic command here. There is just the class that is extending a scene. Well, you can do, let me see if you can do this. Well, you can do Manim minus P for preview, Q for quality, L for low, name of the file, scene.py, and then the animation that you wanted to create. Now, if I run this, I don't remember if the scene is correct or it's not, but yes. So what we have here, we have series of animations that are cached because I have already rendered it before. And all of those animations, they are saved in your temporary animation file. You can see in the Git repository that you have a new directory that is called media, and some, let's say, hidden directory that is PyCache, that is storing the temporary animation that you are creating. And then your output can be found in media, videos, name of the scene, so for instance, animate with Manim, the quality that you chose, 180p for the high quality, and then you have, for instance, the partial movies, and here you can find everything that that has been created by Manim. So I have a few examples here. In this second example, what I am running is a new class. In this new class, still extending the scene, I want to write some text. So in the text is just the object text. I may zoom out a little bit so that it is more visible from the people here in the room. So I am creating a text. Well, the text is just an object that is called text, and I am playing the writing of this text. So when I use self.play, what I am inserting is a new element that will be written on the screen, and the write class is going to simulate the writing in a blackboard. So then what am I doing? I am creating a circle, and guess what? Well, you have the class circle. I am creating a square. You have a class that already introduced, already contains the square. I am creating first the blue circle, and then I am animating. I'm animating the movement of the blue circle. So if I run this thing, we will see that step by step in the following. I'm going to see what this is doing. It's creating a lot of partial animations. And here you have your code. So in your code, well, we had what? We had the first announcement. We have movement. We have the creation of a circle. Then the transformation of a circle. And I am using some sort of ways to show what it does. And well, I suggest you to check all of the examples before diving into the step-by-step guide. So I don't know why this thing is not working. Yes, it is working. Well, this is another example. This is another example. Well, this is an example that can be interesting. We can see that more later. But what I was showing here is how to print mathematical expressions. So in order to print mathematical expressions, let me first show the result of what we have here, and then we go to the, sorry, I don't know why this is not, yes, exactly. So now I am creating this Taylor expansion, and I am going to show what I wanted to convey with this animation. So, and after this short demo, we will go back directly to the basics. So depending, of course, on your machine, the animation may take more or less time. I think there are ways to use, for instance, your GPU to accelerate, to speed up the processing, or you can parallelize, for instance, the partial animations, since they are typically disconnected. They do not require to be performed in sequence, because what is actually happening is that Python is interpreting line by line your code. It is stopping when there is a play or a wait animation. And after that, everything is being put together. And this is just for one scene. Then what you can do is that you can create another scene and use typically what happens is that you use an external tool like a movie maker or something, and in this particular tool, so let me see if it finished, you can join all your scenes together. So for instance, in this animation, it was a little bit more complex. There are 21 so far partial animations. And well, this is the result. So in this result, what you have is that you have an exponential function, and then you have the Taylor series. Well, the Taylor series is that any function can be expressed as the infinite sum of the derivative of the function at an arbitrary point times the shift of this point to the power of n, everything divided by the factorial of n. Well, you can have a Maclaurin series where you just set the initial point equals to 0, which means basically that you can express e to the x as different values depending on the number of n, so the number of functions that you are using. And here I am simulating how this increase of n is approaching the exponential function, so that your approximation becomes more and more realistic. So we have seen a lot of things, but let me just show a little bit what are the basic options that you can use. So we have seen that the basic component is a scene, and scenes are the container of your animation. A scene has two methods for adding a time-dependent variable in your animation, that is wait, in which the animation just stops. It lags for a specified amount of time. By default, a self.wait is inserting a 1 second delay, but you can pass any amount of wait that you want. And the second way to add a time-dependent variable is a play. When you play something, well, you require an animation. So this was the first example that we have seen. Just just creating a new scene that is waiting for 2 seconds. This is not very interesting. The second thing that we have seen so far is using circles, using squares, using tag objects. So what are those things? Those things are the children of the M-object class. So the M-object class is a mathematical object that is inserted in a scene to belong to the animation. There are 5 classes of mathematical objects. You can have shapes, as we have seen together before, circles, squares, dot. You can have text, both a simple text, let's say, without a mathematical expression, or a mathematical text that is in the third category. You can have images, both in bitmap format and in vectorial format, and also user-defined content. All these objects can be found in the geometry package. And a very effective way of using Manim is to periodically check the source code. And in fact, in the source code, well, if you go to the Manim package, and then you go to the M-object directory, well, you can see all the M objects that can be defined. We have discussed about the geometry package, and in the geometry package, well, you have all the examples in the all vector that can be created as a geometrical shape. So you have line, you have regular polygons, tips, rectangles, so rounded rectangles, ellipse, and all of those elements, they come with their own customization. For instance, if you let me create, so here I am creating a square. I am adding the square to the canvas, so to the container, and then I am writing some LaTeX text, and I am adding this text on the screen. So let me run this code. So when you run this code, well, you have this effect. What you can see is that first thing, LaTeX is a LaTeX command. So I have used, let me find it here. I have used /LaTeX. That is the built-in command to render the LaTeX logo. Commands in LaTeX can be escaped with a backslash, but there is no need to do that, because typically it works very well, but sometimes you may encounter some problems. So this is also an accepted syntax. If you just have a double escape in every time that you use a backslash. This second thing that we can observe is that by default, all objects are placed in the origin. So they are in the center of your animation. We can then move the object, and the object can be placed in different ways. So when you use effects like a fade-in effect, or objects transforming into each other, or object appearing out of nowhere. So the two examples that we have seen is that you can add a circle, then you can add multiple objects to the scene. And if you want to animate the creation of an object, well, you can play the creation of the M object. And this is exactly what is shown in this other cell. So in this other cell, let's see what we are doing. We're doing the usual stuff. I am creating a scene. I am defining, sorry, a scene class. I am redefining the constructor. Then I'm creating a square. So when you do a square creation in Jupyter, you can just ask for the signature of the method. So the init signature is that in order to define a square, the only thing that is needed is a float that is reflecting the side length. But you have also other arguments that can be passed. All those arguments are inherited from the base M object class. And these arguments may, for instance, contain something about the color, something about the thickness of the shape, etc. So by default, if I write nothing, the side length will be 2. So if I want to create a square with side 3, I just create the square with, I just pass 3 here. And then I am playing the creation of the square. We have seen before that I have used the tech object to write something in LaTeX. You can use, instead of using the create class to play the creation of an object, when you use a text, there is a nice way of simulating the writing in a whiteboard that is calling the write class. So create is used for shapes and write is used for text. So now let me run this code. I always use quality low just to speed up the process. So my pipeline of working is I try to render in a low quality. Then if I am happy with the results, well, I go with the highest quality. So what have I done here? Well, I have created a square, and then you can see that hello world in LaTeX is simulating someone writing, so word by word, letter by letter in your screen. So let's talk about positioning. There are 2 ways. So once you have your objects, be them the mathematical objects or shapes, and you want to position those, well, you can use absolute positioning. Every M object inherit will and every inherited any children class of the M object class will share the methods to position the object either in an absolute way. You can use coordinates. In Manim, by default, the coordinate system is a 3-dimensional coordinate system, x, y, z, where x, y are the horizontal and vertical coordinate, and the z is the depth of your camera. if you need to explicitly ask for a three-dimensional scene before you use the how to say, the depth coordinate, the z coordinate, because otherwise it will not work. So every time that you specify the coordinate, well, it should be just an array with 0 as the third number. Then you can use methods to edge, for instance, to move objects to the top, the bottom, to the right, or to the left edge. To corner, where you can position the object to the up right, down right, up left, or down left corner. Or relative. Well, relative is can be achieved by using a shift method, where you shift the object to some direction, or next to, where you just place the object close to another object that is referenced in your canvas, so in your container. So this is just to show that by default the grid is using some coordinates where the unit is 1. So of course the unit is 1, and there are from -7 to +7 in a horizontal shape, and from -4 to +4 in the vertical direction. So I already created this. I hope it's cached, because it was taking a huge amount of time. And then we can, yes. So this is the number plane. No, it's not there, but it's okay. So we can emulate this by just creating a number plane and positioning a circle, a square, and a triangle in the number plane. So the number plane is again a built-in function of Manim. So if I run this code, what I am having is background. So the X and Y axes are highlighted. And you can see that the screen is going from -7 to +7 in the X-axis, and from -4 to +4 in the Y-axis. So let's move these elements around. So we said that we can position elements in an absolute way. So I go back here. Then these elements, they are for the moment created anonymously. So there is no object that is referencing the class creation. So it may be difficult to move objects around. So what we can do is instead having something like this, where I pass the C that I create here as a size 2. And then what I do, well, I move this thing to edge. So how do I move it to edge? Well, it's super easy. There are built-in ways, and one of these built-in ways is to just use the keyword up. So you have keyword up, you can have down, you can have right, and you can have left. So if I position this circle to edge left, so what will happen? We will see the animation shortly after. And the circle is positioned to the left edge of your canvas. Let's do the same thing for the rectangle. Sorry, for the square. So now we create a square of size 4. I don't do it anonymously anymore. I just do it with this square, and then I do 2 corner this time, and this time I want it to be positioned to the corner upright. So I just write UR. And now the square is positioned to the upright corner. So what is happening here? Let me use my pen. So here it is happening that there is a buffer. So this is a buffer because I am trying to position the square to the upright corner, and then the Manim is introducing automatically a buffer in order to be, let's say, nicely positioned in the canvas. We can, of course, modify this buffer. And if I remember correctly, I can use this thing by passing buff equals 0, for instance. Let me see if it works. It does. It does work. And so what do you see? Well, you see that now there is no more buffer here. So there is no more safety distance to position this object. It's nice if you use the Pythonic syntax that everything can be cascaded one command after the other. So every time that you run to edge, to corner, shift, or anything, you just return the same object, but shifted or moved there. So what I can do is that after I position the square to the corner, I can then shift towards some direction. So in order to shift towards a direction, you can just for instance, say you want to shift it 4 units down. Well, you say 4 down, and then you want to shift it 4 down and 2 to the left, plus 2 times left. So, yep, I don't know what happened. I don't know what happened. Where am I? Yes, here. So what has happened? The object was placed to the upright corner, then shift 4 units down, and then 2 units to the left. The results, since we used just the self.add method, is only considering the end of the coordinate path that you have installed. So this is basically just the final result. We don't see all the intermediate step. In order to see the intermediate step, we need to animate the moving of the objects. How do we do that? Well, I have said that in order to introduce an animation, we have to use the self.play method. And the self.play method, for the moment, we have only seen it as a way to create objects or to write text. So let me see if this works. So what am I doing here? I am creating a square. The square is already shifted 2 units up. And then I am playing the creation of this square. Another parameter that I introduced right now is the runtime, because everything can be tuned. You can modify the running time of the creation, of the animations, of the weight. So everything is finely tuned. So let's see again, what am I doing here? So the square is shifted 2 units up, and then I am playing the creation of the square, which is already positioned 2 units up. So I am not movement. Then I am creating some text. The text is a LaTeX string. The string is moved to the edge up, and then I am playing the writing of this text. Once more, no movement. I am now creating a triangle. The triangle is scaled. There is you can see all of the methods of manipulating the size of the object in the geometry package. So it's scaled at 60%, and then it's moved to the corner upright. And then I am playing the creation of this circle, moved next to the S1. What was the S1? Was the square in the direction down, so underneath the first square. So for the moment, every play is just yes, I'm sorry. So everything is there. So I am positioning the objects. The objects are already pre-positioned in the coordinates that I have assigned. There is no number plane here because I didn't want the number plane. So I am only animating the creation. So There are several other positioning info that you can use, for instance, the alignment, the centering, the spacing, or the layout of objects. But I leave it to you, because what is more interesting now is animating objects. So animating objects is done typically using the dot animate signal. So you take an object, you use dot animate to create the animation that you want to achieve, and then you specify the series of steps that you want to animate. So let's have an example. Now, in this example, I am once more creating a square. By default is of size 2. And then what I want to play is I want to move the square in the absolute coordinate 3, 0, 0, but I want to animate this move. So I just interpose this dot animate syntax where I do square dot animate dot move to, and I pass the coordinate 3, 0, 0. So 3, 0, 0 is 3 to the left, so the x-axis, y 0, I stay in the y-axis, and 0 is the depth. I am not using a 3D camera, so I'm moving this to the coordinate 3, 0, 0. Then everything can be animated in Manim. For instance, even changing colors is an animation and can be animated. In the second line, I am creating a circle of color blue, and I am animating the setting of the color red. Triangle, I want to animate the scaling of the triangle to the corner, and then I am playing the circle animate.set fill white. So how does the animate work internally? Well, internally, the animate is quite simple. It's basically taking two states, the initial state and the end state. And then Python is interpreting an interpolation method to go from the initial state to the ending state. So basically, when you say self.play square.animate.move to 300, where I have the initial condition 0, 0, 0, I have the ending point that is 300, I have the running time, and Python is interpolating, well, how should I go from 0 to 3 in the amount of runtime that is specified? By default is 2 seconds. I can specify it more. So let's see what this animation is doing. So I go back here, exactly. So let's go here. But I am, so the first square was just created. It was just added to the canvas, so no animation. But I am animating it moving to the right. I am animating the changing of the color of the circle, and then I am animating the triangle scaling up, and then moving at the same time to the bottom right corner. How did I achieve to animate the movement and the scaling at the same time? Well, you just cascade the two modifications that you want to do, and then you scale it up, and then you move it to corner. You pass the dot animate syntax before, and then you just run a single play in order to have this animation together. You can pass as many animations you want together. So for instance, if you want to animate the changing of the circle and the triangle animation at the same time, you just run self.play with the triangle and the circle using the same line of code. So now if you go here, exactly. So of course the animation time now is reduced, because you have the 3 seconds of the square transformation, and then 2 seconds of the animation of both the circle and the triangle. And afterwards, you have a wait. Okay, so nice. Another simple effect that you can use, and is especially useful when you're teaching and then you want to show something that is becoming something else, is the transform technique. In the transform technique, you have one element. It can be any kind of element. It can be a mathematical object, it can be a text, it can be a shape, and you transform it into something else. So here I have a blue circle, I have a green square. I play the creation of a blue circle. You can, of course, now understand that self.play is inherently calling also the self.add. So when you play the creation of an element, the element is already added in your canvas. But if you just do self.add, no animation is generated. So what am I doing here? I am playing the creation of the blue circle, and then I am playing the transformation of the blue circle in the green square. There is a nice thing that I have done here. Well, what I am doing is that I am playing then the animation of green square, so the second one, and I am shifting it to the left. But what will happen here? Well, it will happen here that I have the circle is transformed, and then there is this strange effect that is happening. This is because the transform is not replacing the previous object from the canvas. So right now, after I move the green square, I end up with two green squares that are out of your canvas. And this is because you have another technique that you can use, that is replacement transform, where the second object is completely replacing the first object. And in fact, if you use replacement transform and then you try to move the green square, so to animate the shift of the green square 4 units to the left, what you will end up with is something like this. So circle, then square, and then the green square is moving. Yes?
You cannot transform any object in another one, so there are conditions, right? Number of holes, and so what people do in geometry. So I mean, so what type of objects? Don't you have any restriction?
You don't have any restriction. I can transform an object in, for instance, I can transform a square into a text. It's so what is happening underneath is that the text is a vectorial object. So it has a series of points, and then the square is also a vectorial object. So there is an interpolation function that is used to match all the set of the points in the first object into the set of the points in the second object.
Okay. So there are no restrictions.
No restrictions whatsoever. No. I can actually test it right here.
Show us square to text.
I can show you square to text. So now what I am doing is that I'm creating square to yeah, you can do that. So text is a tech object that is hello again, and then I am animating, okay, moving of the green square, and then what I will do is self.play. Let's transform the green square. Sorry, we need to transform the green square into the text. Yes, and then I do just a self.wait. Let's wait 4 seconds. So there is once everything was cached before, there is just the last partial movie that we have here. So, well, you will see already the transformation. I am moving it here, and then I am transforming it into the text.
Can you maybe slower?
Yes, I can slow down. I can slow down actually to show what is happening. So I can increase the runtime, but so this is the shift, and then this is what is happening. So you see all the points in the first element are transformed into the points of the second element. I can Fabian is right. I can increase the runtime just to show display very slowly. So I just do this. I do runtime equals, for instance, 10. So now the transformation is taking 10 seconds, and it's much slower. It will be a little bit slower. Well, there are 300 frames right now that are being generated. By the way, you can also generate images, still images. So this is the shift, and this is the runtime. This is the slow runtime. If you do it in high quality, it will be very nice. It will be very spectacular. By the way, the second object was automatically positioned in the center. So this is why in the replacement there is also this shift. It's inherent because you are not only replacing the shape, you are replacing the shape with all of the coordinates of the shape. This is actually very interesting in the second part, where we will see how this works with functions, with the plots and the function. And maybe I want to accelerate. I want to go to the functions because it's much more interesting. So this is an example of rotations, and the effect on how this works is clear in the rotation, because depending on the technique that you use, you may end up with some strange effects. For instance, look at the rotation on the left and on the right. So what do you see right now? So there is something different. So both are rotating by pi fourth degrees. Exactly. So the first square is shrinking and then growing, and this is because the animate. So this in the left, I am using the animate syntax, and in the right, I am using an explicit rotation transformation. So the animate syntax, what it is doing is that it is interpolating the first state, the second state, and it is using an interpolation function that has a sort of sigmoidal value. So it takes the first value, it takes the end value. So both the first and the last, they are the same, but they go from the first to the last in a sigmoidal fashion. So it shrinks and then it grows. So the interpolation takes just the initial state, the end state, and it doesn't know anything about the internals. While a rotation is actually constructed with a rotating matrix. So you know the cosine and the sine and the minus sign in the other axis. So it is rotating all of the points of the object. So it is creating as many frames as the quality of your presentation, and then it is actually rotating all of the image. And in the text, well, in the code you have this. So you have a self.play, left square dot animate rotate, and then I have a rotate of the right square with the same angle and the same runtime. So this is why there are many ways to achieve almost the same thing, but the details may matter depending on the results that you want. So this is a way to manipulate formulas that was very interesting. I have used the transformation to transform formulas to transform shape into another shape. But for formulas, you have this thing of transform matching shapes. So if two formulas are formatted using the same number of components, and there is a matching between different components, well, you can emulate the fact that, for instance, you have an equation and you are transforming this equation into another. So you are emulating the teacher writing on the blackboard and then taking one element and moving this element into this other place. Probably visually, it's going to be much easier to appreciate. So I am creating two equations. This is an equation of a squared plus b equals c. And then I want to create r squared equals minus b plus c. So you can see that the plus b here and the minus b here, they are the same. And you can see that the a squared here and the a squared here, they are the same. So there is a matching of the shapes. When you have this matching, well, the effect that you can introduce is this. So you have this, and then you have this. So I want to slow down a little bit the runtime so that it is much much nice. So runtime equals 4, and then I do it runtime equals 4. So there are two equations. These are explicitly defined, and the third one is anonymously. So the equation was, let me write it here, a squared plus b equals c. Then I am doing a squared equals minus b plus c. And then I am doing a equals square root of minus b plus c. So those are the three equations that we have. So now I want to show that this minus b is going here, and that this power of 2 is going to the square root here. And this can be done via using matching shapes. So this first equation is not actually a single equation. It is still a row string, but it contains a squared plus b, then an equal, and then a c. The second equation is containing a squared, then an equal, and then minus b plus c. And the third equation, that is anonymously defined here, is containing first the a, then the equal, and then the square root of minus b plus c. And if we do this transform matching shapes, we end up with this that I will show you here. So let me clear the screen. So we have this effect, you see. So the effect is I have the square, the plus that is becoming the minus there, and then the 2 that is becoming the square root of 2. So this is like emulating the fact that elements can become, if they are matching, they can be transformed into one another. There are also ways to highlight substrings. So if I remember correctly, I can have it here. So text string. So let me check in the math equation. Substring to isolate, exactly. So I can have this kind of things where I want to isolate something. And then I pass the substring to isolate, and I want to isolate the A. So if I want to isolate the A, let me see what is happening. A is isolated. And I can pass, for instance, some special treatment for the A. So in this case, we do not see anything, but we can do, for instance, equation dot so it was oops okay for the moment it's maybe best if we move to the plotting part. So what you can do is, once you isolate a substring here, for instance, you can decide that every time that you match the same substring, you color the substring in a different way. There are some code in my previous cells that we can reuse, but for the moment I suggest probably to show the plots. So plots, this is very nice, because what you can do is plotting data from CSV files or arrays. The most exciting and nice part is that you can use Lambda to define functions or implicit functions, or you can plot directly using a parametric curve, function graph, parametric functions. And okay, the final way is that you can manually just write lines in your graph. So in order to plot, you need to introduce a coordinate system. So your coordinate system is going to be, sorry, I've lost myself. It's here. So you create a coordinate system from the access class. You define a function, for instance, using a lambda expression or using a CSV file. Then you just plot, similarly to what you would do with matplotlib, with axis.plot, passing either your lambda expression or your list of points that you want to achieve. By the way, Manim is implicitly also importing the NumPy library. So you have everything that you inherit from NumPy, from random to NPy sine, cosine, etc. You can then, for instance, match some point to some coordinate in the graph using the coordinate to point primitive, the coordinate to point method. And you can find the y value corresponding to some x value using the underlying function method. So let's show this in action. I have a CSV that is already included in my notebook. And then I am creating the class plot data. I'm reading the file from the CSV. Well, this is not interesting for you, but I am creating just a dict reader. And then I am adding everything to the data X and data Y. This is unfortunately a sort of limitation where you need to divide the X and the Y if you want to plot a function point by point. You define the range that you want for the X and Y ranges. And you just create the axis. You can pass some configuration, for instance, the colors, the numbers to include, and everything. I'm not going into detail in this thing. A simple axis equals axis would have just worked. This is just to show everything that you can add into the axis creation. And then you plot. So the first thing that you want to plot is, for instance, you plot a line graph from the data that you have. So here I'm using the plot line graph method of the axis object. I am adding the axis, the graph, and the label to the scene. So I am not playing anything. And then I am waiting. Then I want to plot some function, and this function is defined using the lambda, using a lambda expression. So my function is basically associating to h of the x the sine of x times 2 times x. I am plotting the second graph using the syntax axis.plot function. I am passing a custom x range and a different color. I am adding a different label. And then for fun, I want to also get the vertical lines to the graph using, again, axis.get vertical lines to graph. And then I want to transform the first graph into the second graph. I want to transform that first label into the second label. And then I want the label and then adding all those things to the canvas. So for the moment, everything in one shot, no. Then I am defining another function, another plot, another label. I am adding some vertical lines to the graph. And finally, I am transforming. So this is an animation. So I am transforming the graph into the second graph, the label into the second label. And I am also creating these additional vertical lines to the graph. Let's see this working. So using the cached data. So there are several animations that are involved here. Partial movie 1, 2, 3 combined into movie file, and then this is the result. So we have created axes with the X range and the Y range that we have shown. The first is a data point that was retrieved by the CSV file. And the second one is this function that I am showing with the label to the top, to the up left corner. So from the CSV, where I also highlight all the points, and then the function sine of x equals plus 2x. So you see once more, any object can be transformed into each other.
Naive question.
Yeah.
So, I mean, I understand to discretize everything, right?
Yes.
And there are points that you move, and so it reminds me of this optimal transport problem. What are the algorithms and how do you move mass? Do you move mass optimally, or what is the principle of transforming one object?
So the principle of transforming one object into the other is we can actually check together the class transform. So if you go here, you go to animation, and then you go, for instance, to transform. So in transform, let's find, for instance, the transform. Okay, there are a lot of transform. So this is what is required into the transform. Well, you can, for instance, transform using axis, using a path function. So by default is none, but you can, for instance, specify a smooth function, a linear function from one point to the other. And
which was used probably
yes,
we were seeing in the earlier thing in these
exactly
lines and
yeah, so there are, this is because there is the straight line, but you can also define your own function, your own transform function.
And if you want, if it's you can the optimal if and so but the masses of the objects, I mean, should have the same size.
No. It just expanded and if needed, or contract or compressed in if needed.
Okay. And you can define your own function and be optimal if you want.
Exactly, you can define your own function. You just pass the path function. So in fact, here, if nothing is set, there is a straight path. And but then you can so for instance, there are several other transformation: clockwise transform, counterwise transform, move to target, and then you can apply pointwise function where every point is actually moved to another point. So maybe here some restriction may arise. But yes, you can apply complex functions. Well, you do not need just a real function. You can also use complex numbers. So it's very another transform method is apply a matrix. So like the rotation that we did before. So for instance, for the apply matrix for the rotation, you need the object to be always the same object, because you are rotating all of the points of the object. So there is it's a biunivocal function. You need all points in the first to correspond to the second, and vice versa. But otherwise, there is no restriction to the domain of the functions that you use. And this is an implicit function example. So I am defining an implicit function as two variables, x, y, and this is hyperbolic paraboloid, if I'm not wrong, because it's x times y squared minus x squared times y minus 2. Should be a hyperbolic paraboloid. Let me see. Something like this. Yeah. So this is a function just defined using the implicit function definition. The color is yellow, and I am adding the number plane and the graph. So number plane and axis, they can be mutually exclusive, but not necessarily. So here I'm using axis in this particular example because I wanted to show the x and the y. Here I am just using a number plane, so a whiteboard with number planes, and here I can I can see the coordinates of all these things. So there are several things that probably we will not have time to do. I want to just show that value tracking and updating functions is super useful, especially if you want to combine several animations and keep track of the evolution of one animation with other shapes or other functions. I will be very fast here. So basically what happens is that consider one animation. and consider, for instance, we have seen before the position being shifted from the origin to the left, or the position being shifted from a point to the corner, or two objects moving one with each other. Now, there is a way to keep track of a value that is called a value tracker. And this value tracker is updated at every frame of the animation. So if you update the value tracker of all the animation, you end up with the possibility to evolve one existing shape that is already painted in your canvas, and to adapt it depending on the value of this value tracker. So for instance, suppose that you want to track a value going from 0 to 10, and then, or maybe, okay, let's make it simple, from 1 to 10, and then have a square increase its size from 1 to 10. So you can do it by setting the square to, by setting the value tracker to track the transformation from 1 to 10, and by setting the square to follow the to be redrawn every time that the value tracker is changing its value. So let's see the end result that I have here. And the result that I have here is this thing, okay? So I'm creating a value tracker. This value tracker will be moved, actually will be animated to track the value of 5. And then I am creating a circle. So this circle is tracking the get value of the value tracker. So value tracker starts with 1. The circle has an initial value of 1. And then I want this simple play to animate the set value of 5. And I want to expect the circle to be adapted when the value tracker is changing. So there is some caveat that we need to see, because we need to always redraw the circle. And to always redraw the circle, we just need to create a circle as usual with the initial value from the value tracker, and pass it as a lambda expression such that it can be always redrawn when the value tracker is being animated. So in fact, when I do it like this, my animation looks like this. And so the initial value is 1, the final value is 5, and I am animating everything from so the circle to grow in size from 0 to 5. For instance, after this first trial, let's add a decimal number. So this decimal number is another object whose value is set to track the get value. I'm also shifting it 1.5 to the up and 1.5 to the right. So if I add this decimal number, for the moment, nothing will happen because it's not added. I want to write it. I want to write the decimal number. So nothing is happening because I do not have an expression that is always being redrawn to adapt its value in order to follow the value tracker. So what I can do is I can do it the same. So I can use the always redraw method, or I can have a special function that is called an updater, where I pass the set value as the current value of the value tracker. So this ensures that at each frame, my decimal number is being redrawn to follow the value tracker. So it starts from 1, it goes to 5. And this is very interesting, especially when you have multiple objects to be following the same value tracker. In fact, after the second trial, let's add an arrow. So the arrow is just a line that starts at the circle get center and it ends as well in the circle, but times the value tracker. So this is just the coordinates. The coordinate is the radius of the circle times its cosine, and times the cosine of an angle that we have decided, so pi fourth, and yeah, the sine of an angle that we have decided. So let's do this. Okay, what happens? I mean, remember with points. Ooh, interesting. I don't know what is happening. I don't know what is happening. So let's use the always redraw technique. Should be good. Okay, there is a problem with this arrow. I don't know why. Play. There is a problem with this this arrow that maybe we will check. We will check later. Okay, let me write this here, because I do not know why it's not working. So that for the people in the notebook, I can check it. I can check it later. I just wanted to finish with some camera settings. So camera settings, they are very useful when you want to show what happens in very specific parts of your graph. So you basically, instead of inheriting just with from the scene class, you inherit from the moving camera scene. You inherit from the moving camera scene, and in this case, you will have access to self.camera.frame.animate. So you can animate, for instance, the camera to go zooming, the camera to go farther away. And I wanted to show this because in this scene, I am plotting the function x and the function sine of x. And I want to see that for small number of x, x approximates the sine of x. So I want to add these two plots to my canvas. I want to have these two functions, and then I want to create a note that can be that can show that this sine of x approximates equals asymptotically the x, where the limit of x goes to 0. So there are some nice things that I am adding here. I'm adding a tangent, I'm adding a dot. You can see that in the code. And then I am adjusting the camera settings to zoom. So I want to set the width to 1.5. You remember the width of the screen? It goes from -7 to +7. So I want to zoom it to 1.5. So very close to just a single unit occupying all of your screen. And then I want to move it to the coordinate 0, 0 with respect to the axis that I am defining in the runtime of 5 seconds. So let's play this thing. It should be a nice effect if we make it work. So there may be several animations here. There is the approximation part. There is the value tracker. So there are 150 frames for the moment because I've used maybe the high quality, no, medium quality here, because I wanted to show a lot of details in this thing. So now let's see what happens here. So what happens is that I have the two functions, f of x and sine of x, and I want to show that when we goes close to 0, the tangent of the sine of x approximates the function of x. So I am using the effect of the camera to zoom in in my graph, and to see that in fact, when x approaches 0, the sign approaches the function x. And this is done by simply having an axis, one sign defined as a lambda expression, one x defined as a lambda expression, and then a tangent point using just the built-in function to get the tangent. So the tangent is updated automatically with a value tracker going from the coordinate 3, if I'm not wrong, yes, the coordinate 3 to 0. I'm animating at the same time the tangent going from the point 3 to the point 0, and the camera animating from the outside, so from the, let's say, original value to the origin. So that said, I don't know if there is a chat message. No, there is no chat message. So that said, if you go back to the repository that I have provided, so what Manim is not, well, it is not necessarily a visualization tool. It's there are other ways to visualize your data. If you want to visualize tool, you can use d3.js. You can use matplotlib if you want to plot data. It is not an interactive event handler. You need to use JavaScript if you want. You need to use other tools to interactively play with Manim. Although it is possible to have an interactive console using the Manim source code. And it is not a movie maker. So you still need a movie maker in order to put all your scenes together. So what is it actually? Well, if you want to investigate some topics that will require not only a bidimensional and instantaneous kind of analysis, well, Manim is very useful because you can very easily animate things. You can very easily animate mathematical objects or shapes. You have built-in capabilities to create plots at super high quality, 60 frames per second, and at 1080p. So I am using it for instance, showing how protocols work. I am using it for showing when there are some functions that interact with each other and where your PowerPoint would be very, 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 very heavyweight to effectively prove your point. And also because it's easy. So once you get the gist of it, it's just a matter of combining your ideas, so what you have in mind, and write some code. The advantage of Manim is also that, I mean, it's Python. So you want to animate the bubble sort. You just create some objects as Manim objects. You practically implement your bubble sort, and then you just add that every iteration a self.play that animates a swap or not in your bubble sort. So it combines very, very smoothly with computer scientists showcasing some, let's say, simple algorithm with mathematicians that want to show how functions evolve as a matter of when the time goes on. And it works very well for all kind of public that doesn't want to invest a lot in learning new tools for how to create animations with advanced tools such as I don't know what exists out there for the animations. So well, that's it. I don't know. Thank you. I don't know if you have some question. So we hear something, but we do not know. Se Marcotti è...
Désactiver les sons.
Yeah, because we hear just a beeping, but we don't hear. Could you animate graph? Yes, of course you can animate graph. We can animate graph, and it depends on what you mean by animating graph. So I can show in the examples from 3 blue, 1 brown. By the way, I suggest you to have a look at its YouTube page. So let me go here. You can animate graphs, for instance, like this.
This right here is what we're going to build to. This
So you see that this bottom part is being animated. Sorry. Yeah. Sorry, a graph, not a plot. Yes, a graph. Of course, you have this. You go to the Manim community. I'm sorry for the misunderstanding. A graph in the sense of a graph. So tutorials and guides, reference manuals. So you, in fact, this is very interesting because you have 2 classes here. You have graph and graphing. So graphing is plotting. Graph is graph. So you have the graph code. So you have digraph, generic graph, so a directed graph, undirected graph, vertices connecting with edges, and then you can extend it with your own. Yes, you can animate graphs. So the only parameters is a list of hashable vertices, the edges. You can add labels, and then you have pre-built-in layout. So spring, circular, Kamada, kawaii, planar, random, shell, spectral, spiral, tree, partite, etc. So the answer is yes, you can automate graphs. You can automate graphs, and by the way, since you can also use CSVs to import your graph content, it's just a matter of reusing what I have did at the basic at the CSV part here. You read your data, you import your data in a CSV format, and then you just put this into the vertices syntax asked for the graph, and you have it. And then you can animate it in the sense moving it or finding some optimal placement, similarly to what can be done with a regular graph manager. So yes, I do not have. Yes, I do have an example. I do have an example of. Let me see. I do have one example of graph animation because I am participating to a project where I asked my students to understand neural networks, and there is a Manim animation of neural networks where you have this effect here, and then you have yes, you have this. You have a multi-layer perceptron where your graph has nodes, and then you are animating the triggering of the nodes in your neural network, and then you are animating also the back propagation where you optimize your weights, and then you are also animating. Sorry, what can you animate? Yes, you can animate this. So the amount of layers, the other layers, the output layers, and this is actually a real neural network that is implemented in Python, and this is a real data set that is used to understand how a multi-layer perceptron with 784 layers, because this is a small matrix is a bitmap where each point has a 0 or 1. I mean, is a value from 0 to 1. And so yes, you can animate graphs. And by the way, here there is a part where, yes, exactly. So you are animating also the triggering of all of the functions. So the advantage is that you can reuse existing code. You just put it into animated in visual format, and then you have it already in your pipeline. Okay. So if you have no more question, I think we can stop it here. Thank you.
Sur l'augmentation qui va être préparée.
Ah oui, il y a cette date, par contre, ça,